The number pi is a mathematical constant, the ratio of a circle's circumference to its diameter, commonly approximated as 3.14159. It has been represented by the Greek letter pi since the mid-18th century, though it is also sometimes spelled out as pi. Being an irrational number, pi cannot be expressed exactly as a fraction. Still, fractions such as 22/7 and other rational numbers are commonly used to approximate pi. The digits appear to be randomly distributed. However, to date, no proof of this has been discovered. Also, pi is a transcendental number, a number that is not the root of any non-zero polynomial having rational coefficients. This transcendence of pi implies that it is impossible to solve the ancient challenge of squaring the circle with a compass and straight edge. Ancient civilizations needed the value of pi to be computed accurately for practical reasons. It was calculated to 7 digits, using geometrical techniques in Chinese mathematics and to about 5 in Indian mathematics in the 5th century CE. The historically first exact formula for pi, based on infinite series, was not available until a millennium later, when in the 14th century the Madhava-Leibniz series was discovered in Indian mathematics. In the 20th and 21st centuries, mathematicians and computer scientists discovered new approaches that, when combined with increasing computational power, extended the decimal representation of pi to, as of 2015, over 13.3 trillion digits. Practically all scientific applications require no more than a few hundred digits of pi, and many substantially fewer. So the primary motivation for these computations is the human desire to break records. However, the extensive calculations involved have been used to test supercomputers and high-precision multiplication algorithms. Because its definition relates to the circle, pi is found in many formulae in trigonometry and geometry, especially those concerning circles, ellipses or spheres. It is also found in formulae used in other branches of science such as cosmology, number theory, statistics, fractals, thermodynamics, mechanics and electromagnetism. The ubiquity of pi makes it one of the most widely known mathematical constants both inside and outside the scientific community. Several books devoted to it have been published. The number is celebrated on Pi Day, and record-setting calculations of the digits of pi often result in news headlines. Attempts to memorize the value of pi with increasing precision have led to records of over 67,000 digits. Fundamentals. Name the symbol used by mathematicians to represent the ratio of a circle's circumference to its diameter is the lowercase Greek letter pi, sometimes spelled out as pi. In English, pi is pronounced as pi. In mathematical use, the lowercase letter pi is distinguished from its capital counterpart pi, which denotes a product of a sequence. The choice of the symbol pi is discussed in the section Adoption of the symbol pi. Definition: pi is commonly defined as the ratio of a circle's circumference c to its diameter d. The ratio c/d is constant, regardless of the circle's size. For example, if a circle has twice the diameter of another circle, it will also have twice the circumference, preserving the ratio c/d. This definition of pi implicitly makes use of flat geometry, although the notion of a circle can be extended to any curved geometry. These new circles will no longer satisfy the formula pi equals c/d. Here, the circumference of a circle is the arc length around the perimeter of the circle, a quantity which can be formally defined independently of geometry using limits, a concept in calculus. For example, one may compute directly the arc length of the top half of the unit circle given in Cartesian coordinates by, as the integral. An integral such as this was adopted as the definition of pi by Carl Weierstrass, who defined it directly as an integral in 1841. Definitions of pi such as these that rely on a notion of circumference, and hence implicitly on concepts of the integral calculus, are no longer common in the literature. Remit explains that this is because in many modern treatments of calculus, Differential calculus typically precedes integral calculus in the university curriculum, so it is desirable to have a definition of pi that does not rely on the latter. One such definition, due to Richard Baltzar, and popularized by Edmund Landau, is the following. Pi is twice the smallest positive number at which the cosine function equals 0. The cosine can be defined independently of geometry as a power series, or as the solution of a differential equation. In a similar spirit, pi can be defined instead using properties of the complex exponential, exp, of a complex variable z. Like the cosine, the complex exponential can be defined in one of several ways. The set of complex numbers at which exp is equal to 1 is then an arithmetic progression of the form, and there is a unique positive real number pi with this property. A more abstract variation on the same idea, making use of sophisticated mathematical concepts of topology and algebra, is the following theorem. There is a unique continuous isomorphism from the group of real numbers under addition modulo integers onto the multiplicative group of complex numbers of absolute value 1. The number pi is then defined as half the magnitude of the derivative of this homomorphism. Properties: pi is an irrational number, meaning that it cannot be written as the ratio of two integers can be its exact value. Since pi is irrational, it has an infinite number of digits in its decimal representation, and it does not settle into an infinitely repeating pattern of digits. There are several proofs that pi is irrational. They generally require calculus and rely on the reductio ad absurdum technique. The degree to which pi can be approximated by rational numbers is not precisely known. Estimates have established that the irrationality measure is larger than the measure of E or Lane but smaller than the measure of Liouville numbers. More strongly, pi is a transcendental number, which means that it is not the solution of any non-constant polynomial with rational coefficients, such as by 5 120ths minus by 3/6 plus x equals 0. The transcendence of pi has two important consequences. First, pi cannot be expressed using any finite combination of rational numbers and square roots or nth roots such as 3 square root 31 or square root 10. Second, since no transcendental number can be constructed with compass and straight edge, it is not possible to square the circle. In other words, it is impossible to construct, using compass and straight edge alone, a square whose area is equal to the area of a given circle. Squaring a circle was one of the important geometry problems of the classical antiquity. Amateur mathematicians in modern times have sometimes attempted to square the circle and sometimes claim success despite the fact that it is impossible. The digits of pi have no apparent pattern and have passed tests for statistical randomness, including tests for normality. A number of infinite length is called normal when all possible sequences of digits appear equally often. The conjecture that pi is normal has not been proven or disproven. Since the advent of computers, a large number of digits of pi have been available on which to perform statistical analysis. Yasumasa Kanada has performed detailed statistical analyses on the decimal digits of pi and found them consistent with normality. For example, the frequency of the 10 digits 0 to 9 were subjected to statistical significance tests, and no evidence of a pattern was found, despite the fact that pi's digits pass statistical tests for randomness. Pi contains some sequences of digits that may appear non-random to non-mathematicians, such as the Feynman point, which is a sequence of 6 consecutive 9s that begins at the 762nd decimal place of the decimal representation of pi. Continued fractions: like all irrational numbers, pi cannot be represented as a common fraction, by the very definition of irrational. But every irrational number, including pi, can be represented by an infinite series of nested fractions, called a continued fraction. A001203 truncating the continued fraction at any point yields a rational approximation for pi. The first four of these are 3, 22/7, 333 106. and 355/113. These numbers are among the most well-known and widely used historical approximations of the constant. Each approximation generated in this way is a best rational approximation, that is, each is closer to pi than any other fraction with the same or a smaller denominator. Because pi is known to be transcendental, it is by definition not algebraic and so cannot be a quadratic irrational. Therefore, pi cannot have a periodic continued fraction. Although the simple continued fraction for pi also does not exhibit any other obvious pattern, mathematicians have discovered several generalized continued fractions that do, such as approximate value. Some approximations of pi include integers. 3. Fractions. Approximate fractions include 22/7, 333/106, 355/113, 52,163 16,604, 103,993 33,102, and 245,850,922 78,256,779. Decimal. The first 50 decimal digits of 3.1415926535897932384197169399375110 A000796. Binary. The base 2 approximation to 48 digits is 11.001001111111111111111111111111111. Hexadecimal. The base 16 approximation to 20 digits is 3.243F6A8885A308D31319. Sexagesimal. A base 60 approximation to 5 sexagesimal digits is 3, 8, 29, 44, 0, 47.